So you are the one who will be the, what was your answer? Let's start with A. Does anybody want to explain why they think that the answer is A? Yes. Okay, so you are saying that the only force is the gravitational force. Okay, so the spin of the object gives it another force. What do you mean? You said that the spin of the object gives it another force. What do you mean by that force? The spin of the Earth gives it another force. What do you mean by the spin of the object giving another force? Sure. I will. So your friend is saying that when we release the object, the rotation of the Earth creates a force. So what is this force? I don't know such a force. That's why I am asking. No, I don't know such a force. The Earth is rotating, okay. Well, so this is our building, let's say. Let's just suppose that this is the rotation of the Earth. So I just release an object from that point. So there is no tangential force. There is no tangential acceleration of the Earth. Earth is rotating at constant angular velocity. So which means there is no tangential acceleration on any point on the surface of the Earth. They move at constant speeds. Since there is no tangential acceleration, there can be no tangential force. There is no tangential force. Okay. So anybody who said B and wants to explain why B? B, we are at B. We are at B. Okay, anybody who thinks that the answer is C and wants to explain why? C, okay. Sure. It looks so different than what I drew, right? Okay, so if you want to study the object. Okay. Okay. No. No. We don't know pseudo forces yet. No, you cannot. You're not allowed to yet. You are not allowed to use pseudo forces yet. Anything you can explain using pseudo forces, you should be able to explain the same phenomena without using them. Okay, so in that case, let's come to D and E, where the big battle will be. So who says it is D? Well, you will be explaining the hurricanes. You. No, you answer the D. Why D? So you are saying that this will have a larger speed. Let's call it V prime. This, let's call it V. You are saying that V prime is larger than V. So? Okay, so let's just say that if when it falls, let's say that everything has moved up to here, will it fall here or here? Will it fall in this direction or will it fall in this direction? This one, here. So you are saying that it will fall here. Those are the guys that think it is D. So the thing is rotating like this. So, okay, the Earth is rotating like this. I'm standing here, I drop something, and so the thing will fall over here on my back. I'm the high building. So this is my foot resting on the surface of the Earth. So it will fall here on my back. Okay, so the E guys, anybody who says that it is E? Come on, there are many people who said it was E. Nobody? Okay, come on, there are how many people? 13 people who think that it was E. You thought it was E? Okay. Why? Okay. So you are saying that in this picture, if you look at this picture, so you are claiming that V prime is less than V. V prime is the speed of the object at the top of the building. So its speed is less than the so you said it was smaller. Okay. Deviate. Okay, so just one warning in general. Also in your quizzes, whenever you are asked the question, show that this is true. Sometimes you make claims, you make all the explanations to prove that it is wrong. Then you conclude that it is true. Without any, I mean, there's no step over there. You just start giving all your arguments, claiming that it is false. Your arguments leads to you to the fact that the initial claim is false, and the answer, hence it is true. To your comment, okay, so you said that these two are attached together. So this should go a larger distance than this one in the same amount of time. Because when the Earth completes one full rotation, well, they complete one full rotation at the same time. This covers a larger distance than this one. So the speed V prime has to be larger than V. Yes. So you are claiming that the answer is A, which was straight down, okay? straight down. Okay, that's another example of all the claims, all the arguments making one claim, but at the final sentence you say, so this, which is the completely opposite of what your arguments are saying. Exactly. Okay, so larger speed. Okay, so forget about the south. Now, tell me this. I'm the building. At the top of the building, I'm releasing the object. So you are saying that, let's just suppose that the Earth is rotating like this. So I'm with the Earth, I'm moving in that direction. If I release this mass from here, will it fall ahead of me or behind me? Ahead of you. Ahead of you. Will it fall ahead of me or behind me? Now, the Earth is rotating like this. On the surface of the Earth, the building is moving in this direction. I release the mass from this height. So, will it fall ahead of me, behind me? It will not fall straight down. Okay, so that is the height of the building is equal to the radius of the Earth. Okay. Okay. Ahead of the object. Now, the thing is you see, the tangential speeds at the surface, at the top of the building, is larger than at the bottom of the building. The force, there is a force acting on my mass, the gravity. But gravity is in the central direction, so it doesn't change the tangential speed. The tangential speed of my mass as it is falling down is always the same, and which is larger than the tangential speed here. Since its tangential speed is larger when it falls down, it will fall ahead of me. It will not fall here, it will fall somewhere over here. This had moved all this tangential distance. Now it moved in this tangential distance, whereas the bottom has moved only this tangential distance because the tangential speed of the bottom of the building is smaller. So it will fall in that direction. Now the last thing is that direction the north, east, south, or west? East, because Earth is rotating towards the east, so it is in the east. So the answer is D. Yes. Who? Well, I don't think he could manage to measure this deviation. Did he? I don't know. So now comes the hurricane. Why do the hurricanes in the northern hemisphere turn in one direction and in the southern hemisphere they turn in the other direction? As you wish. We don't know Bernoulli. No. So why does it rotate at all? You see, if I have that rigid object, I have that difference of velocities in this rigid object also. But no point on this rigid object is trying to rotate relative to the other one. So the same difference in the velocities is here.
But this is a rigid object. Air isn't rigid.
I mean, even if it's a rigid object, the forces will create some tension. Come here. You are not such a rigid object. Rotate around yourself.
Like this.
Yeah, do you feel any tension on your clothes? Such that your t-shirts are trying to rotate in one direction and your pants are trying to rotate in the other direction. So, why not? Just imagine that you are also holding your pockets like this, so that you have the same chain differences in the velocity. The velocity here is different than the velocity here, different than the velocity here. No rotation.
Is there any other explanation for that?
Almost. Any ideas? Any other ideas why we, yes? Even if it was a perfect circle, I think we would still have the same phenomenon. No. Well, the satellites are in a fixed orientation. They don't turn upside down, but they still see the same phenomena. No. Come on, it's different. I mean, even if they are wrong, trying to figure out different ideas is always a good exercise. They can be wrong. Okay, I will leave you with the trying to figure it out. Just a hint. If this is Earth, this is the equator. And as your friend said, the atmosphere is not such a rigid object. I mean, the Earth, the air is rotating with the Earth, but the Earth isn't really exerting too much force on the atmosphere. So what happens to the air as one block of air from the equator moves up? That is the hint. Now let's come to torque. So we had already done the kinematics. We know how to describe the orientation of an object. We had this angle theta. We can describe how that theta changes. We have the angular velocity. We know how we have defined the change in the angular velocity, which is the angular acceleration. Now comes the point in dynamics. What causes the angular acceleration to change? I don't want an answer to the hurricane problem. So what causes the angular acceleration to change? Now, one thing that you should pay attention to, what we are doing now can be applied to problems that we had studied before, like the point mass. We had already studied a point mass m attached to the end of a string without a mass. So we can say, yes? So, okay, we can say that, fine. That's true. Now, on one hand, we can say that, okay, this object is a point mass attached to a string, which we had already studied. We know it's if it's doing central uniform circular motion, we know that it has only a central acceleration. If it is not doing a uniform circular motion, then besides its central acceleration, it will have some tangential acceleration. If you are exerting a force on that object, okay, this is the position R, this is the force. So if this is the angle with gamma, this is the name of that letter. Now we know that the central part of this force will contribute to the central acceleration. Well, it will mainly change the tension here. But it also has a tangential component. So we know that the tangential acceleration is given by the tangential component of the force, which is F times sine gamma divided by the mass of the object. So m times the tangential acceleration is F times sine of gamma. This is one thing we have. So this is just treating this object as a point mass. Well, as this object is rotating, we will, if we assume that this string is not is straight all the time, it is a rigid body. Its shape is not changing, as the whole rigid body is rotating around this point. So we can talk about its angular velocity, which will be 2 pi r over. No, okay. The angular velocity will be 2 pi divided by the period, 2 pi over 2 pi r divided by the velocity, v over r. This is what we already know. We know that on a rigid body, the speed of any point on the rigid body is always equal to omega times r. We can talk about the angular acceleration of the object, and we know that the tangential acceleration of the object is related with the angular acceleration of the object through alpha times r. We know the tangential acceleration, F sine gamma over m. So, no, sorry, the tangential acceleration F sine gamma over m. So on one hand, we have the point mass description. On the other hand, we have the rigid body description. Well, F sine gamma would have been nice if we would just multiply it and divide by r. Now, yes, sorry. So alpha r is F times r sine gamma over mr. Now, the reason why I multiplied and multiplied by r is, if you look at this diagram, F is the length of this vector, r is the length of this vector, and sine gamma is the angle between these two vectors. So F times r sine gamma is nothing but, okay, alpha times r is F r cross F, the magnitude divided by mr. Or we can say that r cross F, its magnitude is equal to m r squared times alpha. So we have such a relation. So if you look at the direction of that r cross f, r cross f is pointing, in this example, r cross f is pointing in this direction. We would expect the tangential acceleration to be in that direction, so the angular acceleration is, okay, the tangential acceleration is in that direction, so you can say that the angular velocity is increasing in that direction also, but that direction is by the right-hand rule pointing in this direction. So if we have a alpha in this direction, angular acceleration in this direction, that, well, in this configuration at least, we will have an angular acceleration in this direction. So if you consider mr squared times alpha vector, in this diagram, in this way of showing it, alpha vector is pointing in this direction. R cross f vector is also pointing in this direction. Furthermore, they have the equal magnitudes and equal direction, so these two vectors are equal. So this combination over here is what we defined as the torque created by this force F. This letter is tau. So the torque on an object, on this point mass, is equal to mr squared times the angular acceleration of that object. This is for a point mass. Now, well, what does this equations tell me? For example, if r cross f is 0 for some reason, it might be that r is 0, but if r is 0, r cross f is 0, so this is kind of trivial. But r cross f can be 0, although r is not 0. If r cross f is 0, this tells me that the angular acceleration should be 0. Now let's come back to our example here. Now, to start it rotating in this direction, like this, to give it an angular velocity in this direction, what I did was, I put my finger here, apply that downward force, so that it started rotating like this, it gained an angular velocity in this direction. Now, if the angular, initially it has 0 angular velocity, after I apply the force, it has some finite angular velocity in this direction. So the angular acceleration during this process points in this direction. So that is the direction of the angular acceleration. When I am applying this force over here, this is r, force is downward, r cross f is in that direction. So this is an example where this r cross f is proportional to the angular acceleration as vectors. Now, furthermore, well, if I exert this same force at the same point, but let's say in this direction, in that case, the r vector is pointing in this direction. The force is pointing in the same direction. So the angle between the two is 0. So if the angle between the two is 0, the cross product of these two vectors is 0. It has 0 magnitude. Well, r cross, the torque is 0. Although I am exerting the same, exactly the same force, the torque is 0, so the angular acceleration is 0. Well, that is what we know, because if I just pull an object by a force such that it's directed through the center of the axis of rotation, it will not rotate. It will slide, but it will not rotate. Or if I just push it. Well, another experience is, okay, so let's see. Let me just attach some weight here. Well, it creates enough torque to rotate it quite easily. If I put it somewhere over here, well, it doesn't create enough torque to overcome the friction. Now let's see. Let us put it over here. The force I'm exerting is the same. It's the same object, the same weight, exactly the same force. The only difference is that I exert some force at this point close to my rotation axis or away from the rotation axis. The force is the same. The direction of the force is the same. the direction of the r vector is the same. In one case, it's just smaller. In the other case, it is just larger in the same direction. The only change is the magnitude. So depending on the magnitude, the torque I create, or that weight creates, becomes much smaller than the torque created by friction forces, the internal friction forces. So the angular acceleration in this case is 0. Now, of course, this is a extended object. This is not just a point source, but we can just imagine an extended object. It is just a bunch of point masses. It is just a bunch of point masses. Each one will feel the forces due to other objects. If you consider the wheel, let's just imagine I exert a force here. Now, if you just divide it into very small segments, each segment will feel a torque. The torque acting on the ith field, ith segment, will be equal to r, the distance of the position of that segment, multiplied by the forces acting on that segment. Well, I can have internal forces, just like in the case of the momentum, the force acting on the ith segment due to the jth segment. All the other segments can exert forces. Or I can have external forces. Then to talk about the total torque acting on my object, it is just the sum of all these torques acting on my object. Well, these are the torques created by the internal forces. They should be 0. Otherwise, if the internal forces create a net torque, it just means that the object starts to rotate on its own, which cannot be. So we only have the external forces, Ri cross Fi external. So this is how you can calculate the forces. In this example, we have only one external force acting on this point only. So in this sum, I have a single term. All the others, in the other segments, there is no external force. So there is no torques due to the other segments. Well, for each point mass, we had just proved that this is equal to the torque acting on that point mass is its mass times its distance from the rotation axis squared. It's the previous slide. It is the mass times the r squared, Ri squared, multiplied with the angular acceleration of that point mass. But since we are talking about rigid bodies, the angular acceleration of all parts of the object, they are equal. So I can write this whole thing as the net torque acting on my object, which I can calculate as the summing the torques creating by each one of the external forces. This should be equal to the sum over mi times Ri squared times alpha. Well, this quantity over here is what we call the I, or the moment of inertia. This is the moment of inertia for rotations around the chosen axis. Now, in this case, let's just assume that my object is rotating around this point. So this is the axis of rotation of the moment of inertia of my object. So what I can write is the torque, the net torque acting on my object is equal to the moment of inertia of my object multiplied by the angular acceleration of the object. This is the exact analog of mass times the acceleration of the center of mass is equal to the external forces acting on my object. This is for translational motion, this is for central motion, or the rotational motion. And both of these should be true for a given object. If an object is doing both translational motion and rotational motion, both of these should be true. I have this is the total external force F external, the ith external, the sum over all the forces. The torque is the torques, sum of the torques created by each one of these external forces. So this is the first law is the analog of Newton's second law for rotational motion. Well, let us do an example. The moment of inertia of a collection of objects around the given axis of rotation is just sum over all parts, the mass of the given part times its distance from the axis of rotation squared. It is the distance from the axis. It's not the distance from a origin or a distance from a fixed point. It is the distance from a given axis, the perpendicular distance, this Ri squared. So if you just imagine a thin rod, let's just take at this moment. So we have a thin rod. I have the chalk. It is free to move in around this rotation axis. Well, it's a continuous mass, so it's not a sum, but I have to first divide it into very small segments. Now, the position of each one of these segments, I can just say, okay, let me take this as x. The width of each one of these segments is dx. If it has a total mass m, its length is L. The mass per unit length is m over L. So this segment of length dx is nothing but m over L times dx. So this is the dm, the mass of that segment. The distance of that segment from the rotation axis, this axis, is nothing but this x over here. So the moment of inertia will be just dm times x squared summed over all possible values of x, but x ranges from 0 up to L. So this is the moment of inertia of a rigid rod for rotations around this axis, around an axis at the edge. This is equal to, well, dm is m over L from 0 to L x squared dx. If you take this integral, this is equal to m over L x cubed over 3 x from 0 up to L. So this will be 1 over 3 mass times L squared. This is the moment of inertia of the rod for rotations around one end. The moment of inertia depends around which axis an object is rotating. So the moment of inertia for rotating around, I don't know, this point, such an axis passing through this point will be different than the moment of inertia that for rotations around this axis. So this is the moment of inertia. Now we need to calculate the torque acting on the system. Well, we have the gravitational force, but gravitational force is also acting on each one of these very small dm's separately. So we have to sum over all of them. But the gravitational force is kind of a constant force. So if you just imagine, now in this example, the dm's all have the same weight. So the torque created on the object will be Ri cross, well, Ri is nothing but x in the x direction. This is my Ri. The weight of the ith mass, the force acting on the ith mass, is nothing but dm times g, which is pointing in the downward direction. So Ri cross dm or dm is the mass of the ith segment. Mass of the ith segment times the g vector. Well, this is just a constant. This is also a constant. Well, this constant I can take out of this summation. mi ri cross vector product with g. Now, the nice thing over here is this combination we already know. This is nothing but the center of mass, the definition of the center of mass. This, for any object, is the total mass times the center of mass of the object. So the torque created by gravity on any object is, here we didn't really make use of the fact that this is a linear rod. This derivation is valid for any object. The torque created by gravity for any object is given by the position of the center of mass times the weight of the object, cross product with the weight of the object. So in this sense, the torque calculated by gravity or any constant force would be simple. If you have a constant force field acting on any point, then it is just like a force, a single force acting on the center of mass. Now, in the case of a thin rod, we had already calculated the center of mass. The center of mass is right at the center, geometrical center, if the mass is uniformly distributed. So the weight is here. This is the weight of my object. The torque is here, or the distance is L over 2. So they are, at this moment, they are perpendicular. So the torque acting on my rigid rod is nothing but L over 2. This is the length of R, times the magnitude of the force is m times g. This is the magnitude of the torque. We know the moment of inertia. This should be equal to 1 over 3 m L squared times the magnitude of the angular acceleration. So we can find the angular acceleration of this object. At this instant, the angular acceleration will change as the object moves. But at this instant, initially it is at rest. I just release it. At that instant, this is the angular acceleration is given by this relation. So this tells me that the angular acceleration is equal to 3 over 2 g over L. This is the angular acceleration. Okay, we can talk about the tangential acceleration of the center of mass once we know the angular acceleration. Tangential acceleration of the center of mass is nothing but alpha times L over 2. L over 2 is the distance of the center of mass from the axis of rotation. So this gives me 3 over 4 times g. This is the tangential acceleration. Well, at this instant, since the velocity of this point is 0, initial velocity, it doesn't have any radial acceleration. The only acceleration it has is the tangential acceleration, which is pointing downward. And the tangential acceleration of the center of mass is 3/4 the gravitational acceleration. Now, the question for you to think is, okay, so the question for you to think is, this is less than g. It accelerates, its acceleration at that instant is less than g. Now, when we were discussing momentum, we said that the mass of an object times the acceleration of the center of mass of an object, this is always equal to the total external force. Now, the total external force acting on this rod is given by m times g. Well, if it was only m times g, this would tell me that the acceleration of the center of mass had to be equal to g. But we had now shown that the acceleration of the center of mass is less than g. But that means that there is another external force, F prime. there should be another f prime in the upward direction, such that the acceleration of the center of mass becomes less than g. So what is that force? It should be there, because on very general grounds, for any system, the acceleration of the center of mass times the mass of the whole system is always equal to the force, the total external force acting on the system. This is always true, whether my object is rotating or not. That is always true. Well, what we have done here is also true. It is valid for objects that are rotating. And we see that the center of mass has this acceleration, less than g. But then this equation tells me that if that is the case, there should be another force acting on my mass, which reduces its acceleration. Okay, that is for you to think for the Thursday.